Hello and welcome back. So continuing on with our parser video series, what do we have up next, Nelson?
Okay, we are going to be taking a look at trees, specifically ASTs or abstract syntax trees. Now, an AST, like we described in the earlier overviews, is a way to abstractly describe your code in a way that makes more sense to your language than just a stream of tokens. So generally speaking, in this particular case, we have some JSON code here, but we can have this code represented in a way that actually makes more sense to a computer than it does to humans. Once we've used all the different tokens such as the brackets or the curly braces and the commas, we've used them to identify the meaning of what we're trying to express, but after that they're kind of extraneous. And what we want to do is we want to represent our data or our code file in such a way that makes sense to the computer directly without having a bunch of these random tokens that don't mean anything to the end result.
Okay.
So the goal is to sort of turn this into an intermediate data structure that can be easier understood by the computer and that can be used to end up with a result. And that result could be anything from executing a program to representing data.
Well, help clarify things for me a little bit, because you kept saying to make it make more sense to the computer. I mean, right now we've got a parser set up. We've got the CS files that the grammar files that we've created, and we've generated CS files, and we've got them into our own application here, the mighty console application 117. But so where do ASTs come in? Because at this point we're actually doing stuff with these code files that we're creating with JSON, the subset of JSON that we made it aware of.
Right, and if you look at our grammar file, what you'll see is a bunch of ANTLR rules interspersed with C# code. Now, this approach is very valid for simple grammars, and this is a simple grammar with 76 lines of code. Mm-hmm. But we don't want to couple the code that takes in the string of tokens and converts them into takes in the stream of tokens and converts them into a result. We don't want to couple that with a very specific result. We want to have this parser generate an intermediate form that can be consumed in many other situations. And in addition, we also see that a bunch of the C# code that we've injected into this grammar is cluttering up the file. Again, not very apparent at 76 lines long, but imagine this grammar file. Imagine that it was actually a grammar file that represented an entire language. We wouldn't want the code that actually compiles that language in the same file as the grammar file. Instead, what we would do is we'd have the grammar file do something very specific. It would match tokens and return some sort of intermediate form that other grammars can understand and perform actions with.
Okay.
And in ANTLR, you do that with their built-in ASTs, or abstract syntax trees, where you can have your grammar output a tree. And what I mean by a tree is the tree data structure. So you have a node that has a bunch of children and so on and so on.
Okay.
So the way that you do that is on the top of your grammar file, after the actual definition, you go ahead and give it some options. So we're going to say options. And at the moment, you'll see that in our generated lexer and parser, or specifically our generated parser, if you look at, for example, the object property rule, notice how it returns void. Okay? Mm-hmm. So are we noticing that?
Yep, I notice void.
Okay, sweet. Now watch this. If I say output equals AST, and of course I fire up my little helper application, mm-hmm. ANTLR builder, and then I do a space control S.
Yeah, so it'll pick it up.
Yep. Now look at this.
Hoo-hoo. So an AST parser rule return scope.
Yep. So now all of our methods that are generated from all of our parser rules actually return data. They return an AST.
Nelson, that was actually a successful magic trick you just performed.
Too bad I didn't say the words. Did I say
I know. No, you didn't say it, because it would have been awesome if you'd been like, you see this is void? See? All right, watch this magic trick.
Yeah, well, if I had said magic trick, it would have blown up.
Yeah, probably. Okay.
So yeah, so now that this returns a tree, and we can do something with it right here because this file method. Remember how we have this partial class basic JSON parser with the public method run, and we're invoking the file method.
Mm-hmm.
We can say var tree equals file. Now let's go ahead and set a breakpoint here and hit F5. So let's look at what our parser rules returned now that we've told ANTLR we want to return ASTs.
Nice.
What it has actually returned is a complete flattened list of all the tokens that matched. If I were to go in the immediate window and do a common tree, and I'll explain this in a second, tree.tree.to tree string and oh, come on. Intermediate window fail. Let's just bring common tree into scope. It's in ANTLR.runtime.tree is where it is. Okay, now that I have that using statement there, I'll be able to use my intermediate window to do what I want it to. Of course it doesn't. IntelliSense.
There we go.
Look at this. So this is a string that represents our tree, and it is a completely flat tree. So I want to step back a second and actually talk about what the format that it actually will return in, because that's very important to sort of debug your trees as you build them. Mm-hmm. The format that ANTLR prints out trees with looks very similar to Lisp. So if we have a flat tree with 2 leaves, we would have 1 and 2. Or sorry, 1 and 2. So this is a tree that has a root element, and it has a 1 element under it, and it has a 2 element under it. Now, if we wanted to represent something a little bit more complex, we could say 1, 2, 3, 4. What this syntax means is that you have the root element, you have a 1 element, you have a 2 element, and then underneath the 2 element, you have a 3 element, and you have a 4 element. So the way that ANTLR will actually print out a string representation of the tree in a hierarchy is using these parentheses to denote children to the preceding tree element. Does that make sense?
Yeah, I mean, if 1 had children, then right after 1 would have been an opening parenthesis, and then yeah, stuff inside that.
Yep.
Exactly.
And then that would give, stuff to right there, mm-hmm. which messes up our formatting here.
There you go.
So you'll notice right off the bat that when we run this, we get a completely flat tree. And all of the tokens get turned into tree nodes. That's another very important aspect to how ANTLR trees work. Every one of these is an individual token, and they all get turned into tree nodes. So let's see about actually changing up the way we output our tree in such a way that it will make ANTLR actually create a hierarchy instead of just a flat list. For example, on our object rule, we really don't want these curly braces or these commas. So we can go ahead and get rid of them. What I just did was I removed these tokens from being sent into the tree that ANTLR generates. So if I were to run this again, we would no longer have those tokens. That's one way to get ANTLR to change the way that it outputs tokens. Another way is, and we're probably not going to be using this way, but I still want to express it, is what if we wanted to create children for example, let me find a good example. I might be failing here. Let's just try that. Oh, that's not going to compile, is it? All right, let's leave off that example for a second. What the other syntax that you have when doing tree rewrites, which I'll talk about in a second, is this syntax. This syntax specifies that a particular node should become the parent of the tree, of that particular leaf of the tree. But we don't really want to do trees this way. And the reason is we don't have a lot of flexibility. The only thing we can do inline is remove elements or make elements as the parent. Another way to do it, and the main way we're going to be doing it, is with rewrite or tree rewrite rules. And tree rewrite rules are going to be rules that follow this symbol. And so let's see what we can do with this. I want there to be an object token. Object has meaning inside this JSON language. And I really want us to create a tree node that has the word object in it. It's not going to be a token that's matched to any particular piece of text. It's going to be an arbitrary token that just has meaning inside of our grammar. So what I'm going to do is I'm going to forward declare this token in my token section up at the top of the file, and I'm going to say object. And I can also throw an array as well. I want object and array. I want the fact that we identified an object or an array to be represented inside of our tree. So let's see how we can do that. How we can actually, not only can we omit tokens or make tokens the root of a particular tree, we can actually go ahead and completely change the way ANTLR goes about creating trees by using this syntax. We can say, we want this tree to follow. Then we could say, we want, in this particular alternative, we want this tree to follow. So we've inserted a new token into our tree. Furthermore, we have created a new child, or a new parent tree, a new grouping. So now if we run this again, the tree that we're going to get is going to look a little bit better. Not so much better, but still. we have our object, hey, and then array.
Okay.
The reason that's happening is that oh, right. You see anything wrong with this, Jason?
Yeah, array.
Yeah. So basically this is saying, okay, if this alternative matched, turn the tree into a new child because of this symbol, starting with the object token, followed by all of the tree nodes that were retrieved in the object rule. So now if I were to run this, hey, look at that.
Awesome.
We've created a bit of a hierarchy. We have our object, hey, and then inside of that we have our array, and then another object, and so on and so on.
Very nice.
So we've actually rewritten how that works. So I just wanted this video just to be a quick overview of what we're kind of going to be doing. In the next video, we can go about actually stripping out all of this action code.
Okay.
Finishing up our rewrite syntax, and yeah, moving from then.
Awesome. Wait a minute. Moving from then? Or moving from there? Awesome. Okay, so with that, ladies and gentlemen, that will wrap this video up, and we will see you in the next. Thanks a lot.